So hello everyone. In the last part, we have seen that what is Poisson's equation and what is Laplace equation. So Laplace equation is del square v equals to 0. Now we are going to see that the solutions of the Laplace equation. So we have Laplace equation equals to del square v equals to 0. In spherical coordinates, we can write it as 1 upon r square del upon del r square into del v upon del r plus 1 upon r square sine theta del by del theta into sine theta del v by del theta plus 1 upon r square sine square theta del square v upon del square del phi square equals to 0. So how can we solve this equation? We are going to solve this equation. We have two methods to solve this equation. One method is by using separation of variables, and the other method is by using Green's function. In this part, we are going to see it by using separation of variable. So let's solve for some special cases, like for some simpler cases. For case 1, in case 1, we are going to assume that our v is only a function of Vr and theta is only a function of Vr. That is, it is independent of theta and phi. So if v is independent of theta and phi, then this term becomes 0 and this term becomes 0. So we have 1 over r square del over del r into r square del v by del r equals to 0. If v is only a function of r, then del by del r is equals to d by dr. So we are, this 1 by r square goes to RHS, becomes 0. So we have d by dr is equals to r square dv by dr. From here we can say that dv by dr is equals to a upon r square. From here we can say that v is something minus a over r plus b type. Okay, now let's move to the second part. In second part, we are going to have, we assume that v is function of v, r and theta. We are going to assume v has azimuthal symmetry. So in this, what we are going to have, only this term 0. We have both this term. So we have 1 over r square del over del r into r square del v by del r plus 1 over r square sine theta del over del theta into sine theta del v by del theta. So what we are going to do in this method is, we are going to assume v is a function of product of two functions, that one function is only dependent on r and the other function is only dependent on theta. This method is used as, it is called as separation of variables. So if we plug in this equation and then if we do some manipulations, then we are going to get our solution, which is equals to Vr theta is equals to L equals to 0 to infinity ar to the power L plus b bl over r to the power L plus 1 into pl cos theta. If you all want to see a derivation also, then write me in the comment section. I am going to make a video on that also. So now let's dive into this solution part, because this is important. We have to learn this solution and we have to directly use it in the problems. Okay, so in this problem, this is that r as r, this, and this is theta. Okay, so this is called a Legendre polynomial. So let's see what is, let's see what is Legendre polynomial. Okay, Legendre polynomial. So the value of Legendre polynomial is given as like this: p x p of Lx is equals to 1 over 2 to the power L into L factorial d xl into x square minus 1 ka power L. So here we have x equals to cos theta. So first calculate what is this for different values of L. For plugging L equals to 0, L equals to 1, and then after that substitute x equals to cos theta. So we get, try to remember some of the initial things like what is the value of P naught. So P naught is 1. What is the value of P1x? That is equals to x. So what is the value of P1 cos theta? It is equals to cos theta. What is the value of P2x? It is equals to 3x square minus 1 by 2. Okay. So similarly we have P3. P3x equals to 5x cube minus 3x by 2. Try to remember what is the value of P0x, P1x and P2x. Rest if needed you can calculate this by using this formula. Now let's see what is orthonormality of Legendre polynomial. In some of the problems we are going to use this also. So let's see here itself. Integration of 0 to pi PL cos theta into Pn cos theta into sin theta d theta equals to 2 over 2l plus 1 into delta Ln. So this delta Ln is 1 when L is equals to n and 0 when L not equals to n. So if Pl equals to n, we are going to have 2 upon 2l plus 1, and if it is not equals to, then we are going to have 0. So now let's see an example so that you can understand better. Suppose we have given a sphere of radius r and a spherical shell of radius r, and the surface potential, and the potential at its surface is V0. So we have to calculate what is V inside and what is V outside. Okay, so we can say that V inside is equals to summation L equals to 0 to infinity AL r to the power L plus BL over r to the power L plus 1 into PL cos theta. We have derived it to, we have seen here what is the solution. So the solution is this AL r to the power L plus BL over r to the power L plus 1 into PL cos theta. Similarly, we can say that V outside is equals to L equals to 0 to infinity CL r to the power L plus some DL over r to the power L plus 1 into PL cos theta. Now apply boundary conditions to it. First boundary condition, V should be finite. Okay, so at r tends to 0, V should be finite, but in V in we have this term goes to infinity. So to make V infinite, what we have to do? We have to make BL equals to 0. So this simplifies V in. Now the V in becomes equals to 0 to infinity AL r to the power L into PL cos theta. Now similarly for r tends to infinity, we are going to have this term tends to infinity. So to make this V out finite, we have to make CL equals to 0. This gives V out equals to summation DL over r to the power L plus 1 into PL cos theta. Now apply second boundary condition. V should be finite. Okay, V should be finite. So V should be, in the first part we have applied V should be finite, and in the second part we apply V should be continuous. Okay, so V in at r equals to capital R equals to V out at r equals to capital R should be equals to V0. So now we applied continuity at surface. So from here we are going to have summation L equals to 0 to infinity AL r to the power N into PL cos theta equals to summation L equals to 0 to infinity DL over r to the power L plus 1 PL cos theta equals to V0. So now let's see this part. Okay, so let's see this part separately. So we have now write this by opening sigma. Okay, so this is a0 r to the power 0 p0 cos theta plus a1 r to the power 1 p1 cos theta. Similarly, a2 r to the power 2 p2 cos theta. It goes on equals to d0 over r to the power 1 p0 cos theta plus d1 over r to the power 2 p1 cos theta, and similarly it goes on. So to make both terms equal, what we can do, we can make this coefficient equals. Okay, consecutive coefficient. So from here we can say that if al r to the power l is equals to dl r to the power l plus 1, then this both the term becomes equal. Okay, so from here we can say that dl is equals to al into r to the power 2l plus 1. This is our first equation. Now let's see the second part of this equation, that is equals to v naught. It is equals to v naught. So now let's solve this thing. Okay, so al we have al r to the power n into pl cos theta equals to v naught. Now write again by opening sigma a0 r to the power 0 p0 cos theta plus a1 r to the power 1 p1 cos theta plus so on. In the right hand side we can write it as v0 p0 cos theta, because we have seen that p0 is equals to 1 plus 0 times p1 cos theta plus 0 times p2 cos theta, so on and so forth. So to make the both terms equal, what we can do, that we can equate this first terms only. So from here we can say that a0 r to the power 0 is 1 and p0 cos theta is also 1. So we have a0 is equals to v naught, and remaining all the terms a1 equals to a2 equals to and so on, it is equals to 0. So we can write it as al equals to v naught if l is equals to 0, and it is 0 if l not equals to 0. So from here, so let's put this good. So we have this, and we also have this equation dl equals to al into r to the power 2l plus 1. So we have dl equals to al into r to the power 2l plus 1. So from here we can say that dl is equals to v naught into r to the power 1, because for l equals to 0 it's v naught r. If l is equals to 0, it is equals to 0 if l not equals to 0. So from here we can say what is v in and what is v out. V in is equals to, from l equals to 0 to infinity, al r to the power l pl cos theta. So al is only defined for l equals to 0, and for else it is 0. So it is equals to v naught into r to the power 0, that is equals to 1, and p 0 cos theta, that is equals to 1. So v in is v naught. And what is v out? V out is summation l equals to 0 to infinity dl over r to the power n 2l plus 1, sorry, r to the power l plus 1 pl cos theta. So it is equals to v naught r over small r, for l equals to p naught 0 cos theta, that is equals to 1, and for else it is equals to 0. So what we get, v in is equals to v naught and V out is equals to V naught capital R over small r. So now that's it for this video. In the next video we will try to take some more examples.